Verifying trigonometric identities. How to verify a trigonometric equation. To verify a trigonometric equation, we simplify one side, usually the more complicated side, until it matches the other side. You can also work on each side separately until you get them to match. Now note, there are often many different approaches you can take to establish a trig identity. If you thought about a different way, ask so we can discuss it and make sure you're on the right track. In this first example, we're going to verify cosecant theta tangent theta equals secant theta. So before we start, I want to make clear you could see the word verify, establish, or prove, and they all mean the same thing. So we're going to take one side of the equation, usually the more complicated side, so I would say that's the left-hand side here, and we're going to use either algebra or trigonometric identities to rewrite it so that it equals, in this case, the right-hand side. So we start with the left side, so I'm rewriting it, and this is equal to 1 over sine theta by the reciprocal identity, and then sine theta over cosine theta by the quotient identities. So I've rewritten cosecant theta and tangent theta. Note that I've continued to use an angle and the same angle, theta, in each trig function. I don't want to just start writing 1 over sine, sin cos. I have to include an angle every step of the way. So now this is equal to 1 over cosine theta, because the sine theta over sine theta cancels out to just 1, so I have 1 over cosine theta left, which is secant theta. So that is my answer. I'm not going to box in secant theta. I already knew that's what I was going for. If I were going to box in anything, it's the whole entire answer, or all of the work is the proof that verifies this identity. In this example, I want to verify 1 minus sine x all over cosine x equals cosine x all over 1 plus sine x. Now I would say that neither side looks particularly more complicated than the other. So we can take either side just to mix it up. Since last time I chose the left side, this time I'm going to choose the right-hand side. So I'm going to rewrite the right-hand side. So here I have cosine x over 1 plus sine x. And I don't have any trig function squared here, so I can't use Pythagorean identity. So if I look at what I'm aiming for, I can see I'm aiming for 1 minus sine x over cosine x. And that might be a hint that what I need to do here, the strategy I'm going to use, is multiplying by the conjugate. So in the denominator, I have 1 plus sine x. So what I'm going to do is multiply both the numerator and denominator by 1 minus sine x, the conjugate of the denominator. So I have to multiply by 1 minus sine x over 1 minus sine x because it's like multiplying by 1. So now here, on the top, I'm not going to distribute in the cosine. I'm going to go ahead and leave it separate. So I have cosine x times 1 minus sine x, that has to be in parentheses, all over. Now in the denominator, I am going to go ahead and distribute. So I'd get 1, that's first, and then outer is minus sine x, inner is plus sine x, and then last is minus sine squared x. So you can see that in the denominator, the minus sine x plus sine x canceled, and that's always going to happen when we multiply by a conjugate. So we really didn't need to show that part. I'm just being very thorough here. So here's where I'm at. Cosine x times 1 minus sine x all over 1 minus sine squared x. Now let's go ahead and take a look at where we're at and where we're headed. We're trying to get it to look like 1 minus sine x over cosine x. Well, the denominator here, 1 minus sine x, can be rewritten using a Pythagorean identity as cosine squared x, and then one of those will be able to cancel with this cosine x on the top. So I have cosine x times 1 minus sine x all over cosine squared x. So I'm going to label right now, how did we get from here to here using the Pythagorean identity? Sine squared x plus cosine squared x equals 1. So that means that cosine squared x is 1 minus sine squared x. So now I can go ahead and cancel cosine x with one of the cosine x's on the bottom to end up with what I know I needed to end up with, 1 minus sine x over cosine x. So again, all of this work, all clearly showing every step of the way, is the answer. We are verifying. In this example, I want to verify this left side, this sum of quotients of trigonometric functions here equals simply 2 cosecant alpha. So the left side is clearly the more complicated side, and if you can see right now it's 2 quotients, and in order to combine it together to get one function, I'm going to need common denominators. So I'm going to rewrite the left hand side, leaving a little bit of a space next to each one. So here are my 2 quotients, and for them to have common denominators, I'm going to need to multiply this left-hand denominator by sine alpha, which means I need to multiply the numerator by sine alpha. So I'm going to put a sine alpha multiplied in the numerator and a sine alpha multiplied in the denominator, which means I need to put parentheses around this binomial. And then over here, if the denominator is sine alpha, I need to multiply by 1 plus cosine alpha on the top and on the bottom to force common denominators. So parentheses, 1 plus cosine alpha, and then I need parentheses, 1 plus cosine alpha. Alright, so now let's go ahead and rewrite this as sine squared alpha over 1 plus cosine alpha sine alpha, and then plus over here we have that same denominator, sine alpha 1 plus cosine alpha, and then here if I multiply everything out, these are not conjugates, so they're not going to cancel. I'm going to get, first is 1, outer and inner are both cosine alpha, so that's plus 2 cosine alpha. And then last is going to be cosine alpha times cosine alpha, that's cosine squared alpha. So now, forgot parentheses, let's go ahead and combine these together through the same denominator. They combine to be one fraction, so we have sine squared alpha plus 1 plus 2 cosine alpha plus cosine squared alpha all over sine alpha times 1 plus cosine alpha. Woo, it's a big one. Alright, so let's see what we have. In the numerator, we have a sine squared alpha plus cosine squared alpha. That's an identity that equals 1. So my next step here, I'm going to pull my work up to the top. This is equal to the sine squared alpha plus cosine squared alpha is 1. And there's already a plus 1 there. So it's 1 plus 1 plus 2 cosine alpha over sine alpha 1 plus cosine alpha. Well, 1 plus 1 is 2, so we get 2 plus 2 cosine alpha over sine alpha 1 plus cosine alpha. Alright, we're almost there. So in the numerator, they both have a 2 in common that I can factor out. So I have 2 times the quantity 1 plus cosine alpha over sine alpha times 1 plus cosine alpha. Now that this is a product, 2 times 1 plus cosine alpha, and this is sine alpha times that same binomial, now I can go ahead and cancel those out. The same thing over the same thing is 1. So 2 over sine alpha is the same as 2 cosecant alpha. And that's what we were aiming for at the very beginning. So all of this, these two quotients involving trig functions simply turned out to be 2 cosecant alpha. But there was a lot going on. There's a lot of potential for mistakes. So a lot of times students want to start canceling when they can't cancel terms because the only way we can cancel is if I have products, is if I have factors to cancel. So anytime there's a plus, so there's a plus here, this cosine and like this cosine don't cancel. And that's the most common mistake that students make is algebraic mistakes. In this example, I want to verify 2 cosine x minus secant x is equal to cosine x minus tangent x over cosecant x. So I'm going to start with the right-hand side. So here we have tangent x over cosecant x is the part I'm going to start with, because I'm going to rewrite tangent x as sine x over cosine x. So this is equal to cosine x minus sine x over cosine x over, now cosecant x is 1 over sine x. So I have cosine x minus sine x over cosine x times the reciprocal of 1 over sine x is sine x over 1. So instead of dividing by a fraction, I multiply by the reciprocal. So that gives me across the top a sine squared x. So this equals cosine x minus sine squared x over cosine x. Alright, so now I can rewrite sine squared x using the Pythagorean identity. So I'm going to go ahead and bring this up here. So this is equal to cosine x minus, on the top I have 1 minus cosine squared x over cosine x. And now, because I have 1 term in the denominator and 2 terms in the numerator being subtracted, I can split this up as 1 over cosine x minus cosine squared x over cosine x. So I have cosine x minus, and I'm going to put parentheses, 1 over the denominator, 1 over cosine x, minus cosine squared x over, cosine x. Alright, so how does that help us? What do I have? So I have cosine x minus, inside I have a secant x if I rewrite 1 over cosine. And then here, one of the copies of cosine will cancel, so I will have left just a single copy of cosine x. And now this negative is going to distribute to both terms here. So I end up with cosine x minus secant x plus cosine x for a total of 2 cosine x's. So that's 2 cosine x minus secant x. Whew, alright, that was a lot of work. So these problems are really just practice. There might, absolutely be other ways to go about this problem. So again, if you were thinking about another route, definitely ask me, but this is one way that works, and I want to try to cover the different types of strategies here. So splitting this up as 1 over cosine x and then minus cosine squared x over cosine x, that technique is a good one to keep in your back pocket. On this example, we want to verify that tangent x minus cotangent x over tangent x plus cotangent x is equal to 2 sine squared x minus 1. So I'm going to start with the left-hand side. So here we have it, and I'm going to start by rewriting cotangent x, each of them, as 1 over tangent x. So here I've replaced each of those with 1 over tangent x. And now the strategy that I'm going to use is I'm going to clear fractions. So here in the numerator and in the denominator, I have a term with a denominator of tangent x. So what I'm going to do is multiply the entire numerator by tangent x and the entire denominator by tangent x. So that tangent x in the numerator and denominator, they cancel. It's like multiplying by 1, so that's why I'm allowed to do it. But what I'm going to do with each tangent is distribute into each term. Notice I included parentheses because that tangent has to distribute. So what I'm left with is, if I bring this up here, in the numerator I have tangent squared x minus 1, and in the denominator I have tangent squared x plus 1. And the second I have trig function squared, especially involving ones anywhere, I should be thinking the Pythagorean identities. So the one that I'm thinking of off to the side, I'm going to remember that secant squared x is equal to tangent squared x plus 1. So I'm going to replace this denominator, which is two terms, with the single term secant squared x. So I'm going to leave the numerator as tangent squared x minus 1, but the denominator is going to become secant squared x. So how did that happen from here to here? It was this identity. And now I'm going to go ahead and use that same technique from before. Since this is one term in the denominator, I can split into two different terms, and if I look at what I'm going for here, I'm going for two terms being subtracted. So I have tangent squared x over secant squared x minus 1 over secant squared x. And now let's go ahead and see what we have to work with. So I have tangent squared x, so that's sine squared x over cosine squared x over 1 over cosine squared x, and then minus 1 over cosine squared x. So since this fraction on the top, or this quotient on the top, has a denominator of cosine squared, and this one has a denominator of cosine squared, when I multiply by the reciprocal, I'm going to get just sine squared x minus, and right here, when I multiply by the reciprocal, I'm going to get cosine squared x. So we are close, but not quite there. We're starting to see a sine squared x involved. The last step is going to be replacing this cosine squared x with a Pythagorean identity. So we're going to have to make a little space here. So this is equal to sine squared x minus cosine squared x is 1 minus sine squared x. And this negative will distribute, so I get sine squared x minus 1 plus sine squared x for a total of 2 copies of sine squared x minus 1. So this was definitely a long problem as well. The strategy here to take away is the idea of clearing fractions. So the two fractions that are involved both had a denominator of tangent, so I can multiply both the top and bottom by tangent because it's a clever way of multiplying by 1.